Hey Physics 30s, it's me, Mr. Jukely again. We are now on Unit 6, Lesson 5. This one's all about fission and fusion, so that's fission with an I and fusion with a U. Um, and honestly, one of the big ideas from this, one of the big things you can remember, is when you have a fissure, that's fissure with an I, that means it's a break or a split and things fall apart. So with fission, we're starting with a bigger nuclei and it's splitting apart into smaller nuclei. With fusion is when things come together. So when two things fuse together, you take two smaller things and they make a bigger thing. And that's one of the really big ideas from this, what fusion is and what fission is. Fission breaking apart and fusion coming together. So this is a bit of a left-hand turn from that, sorta, but something that we should know about anyways. So artificial transmutation. Now, if you remember what transmutation is from like 1 or 2 lessons ago, it's when the type of nucleus that you have changes. So in other words, the type of or the number of protons you have changes. So you're changing the type of nucleus, you're changing exactly what it is. Artificial transmutation then, so the artificial part of it means it's done by humans. Which is kind of neat thinking about that. So that's the process of changing the type of element that we have, the type of nucleus that we have, then by bombarding it with high energy particles. So artificial elements and isotopes, they're ones that are not normally found in nature, and you can usually identify them on your periodic table because they don't have, in their atomic masses, they don't have any decimal places. So for example, carbon is 12.01, so lots of decimal places. That is the average of all the naturally occurring isotopes of carbon, whereas, let's find one here, find one that's easier to spell. Bohrium, I was looking at Darmstadtium, which I have a hard time saying, obviously, so I'm not going to even try writing that one out. It has a mass of, where'd bohrium go? It's number 107, 264 in brackets, and that's because that's the artificially transmutated one. That's probably the only one that they've ever made of bohrium. So Rutherford's the guy who started this all off. 1919, he was the first scientist to artificially transmutate an element, which is pretty cool. Now Rutherford, if you remember back to the last unit, Rutherford, what we know of him is he was really famous for blasting alpha particles at gold foil. What we know about scientists, what we've learned through Millikan and a few other people, they often kind of do the same thing over and over. So Millikan, parallel plates a whole bunch of times. Millikan loved parallel plates. Rutherford apparently loved bombarding alpha particles and stuff. So in this case, he bombards an alpha particle at nitrogen-14 gas. Now nitrogen-14 is a very, very stable gas. It's like 70% of our atmosphere. So what happens with this is I am taking my alpha particle. Let's see. Nope, got that a little bit backwards. The 4 goes up top. That's our mass number. The 2, that is an ugly 4. Let me fix that. Okay, wait, there we go. Excellent, there we go. And then it reacts with nitrogen 14, so 14 and 7. And could you guess what this produces? So let's see, law of conservation of nucleons says whatever it produces is going to have 18 nucleons. Law of conservation of charge says that it's going to have 9 protons. Something with 9 protons makes fluorine. So it actually makes fluorine 18, which is very unstable. So immediately decays into a proton and something else. Hey, could we figure out what that something else is? So I'm taking fluorine 18. I'm saying that it is going to break apart into a question mark plus a proton, and a proton has a mass number of 1 because it's made out of 1 proton, and a nuclear charge, or a charge of 1, because it's a proton. So let's see, conservation of charge has to be 8 protons in this missing thing. I could already tell you it's, well, I'll let you figure it out for a second there. And then let's see, this is going to be 1 plus 17 equals 18. Perfect. So law of conservation of nucleons makes sense. Have you figured it out yet? I'm going to ditch that question mark. It's going to make oxygen 17 and a proton. Pretty neat. So law of conservation of nucleons, laws of conservation of charge, all over the place here. So after this, people started to use particle accelerators, which actually there's a whole lesson on that's coming up fairly quick here. People started to use particle accelerators to essentially smash things together and see what happens. We'll talk about that more as we go through. Turns out all the elements beyond uranium are actually artificial, which means none of them are really stable. So yeah, check it out on your periodic table. It's kind of neat. There's a whole bunch that never ever ever show up in nature, but humans have created. In 2015, 4 new elements were discovered. They're the ones highlighted in yellow. So UUT, UUP, UUS, and UUO. The UU, I forget exactly what it stands for, but it means it doesn't have a name yet. That being said, this is an old picture of this. And I thought this was really interesting. The international guidelines for choosing a name say that it can be named after a mythological concept, a mineral, a place or a country, a property, or a scientist, according to IUPAC. That's the International Union of Pure and Applied Chemistry. So while that is fairly broad, it is also kind of narrow at the same time. Like if you discover an element, you can't just name it after anything you feel like. That being said, each of these elements now have names. This is just interesting stuff, to be honest. There's a 5-month period of public review before the names become official. So here are the actual names: Nihonium, Moscovium, Tennessine, and Oganesson. For those new elements that were discovered in 2015. And the next thing is like my favorite thing. This guy's just so happy. This person worked at the Riken Institute, and apparently, when I was reading up on this, this is the first element on the periodic table that was found in Asia, and I just absolutely love how happy this person is. This picture is just a picture of pure joy, showing off him and his team's new discovery. Absolutely love it. Okay, so let's check this out. We've got ES 253. It is being bombarded, I believe that's Einsteinium, by the way, is being bombarded by a particle. As a result, MD 256, I believe that's Mendelevium, 256 is artificially created and a neutron is emitted. Determine the identity of the unknown particle. Okay, so what we need to do is set this up in terms of a nuclear reaction or a nuclear equation. So let's see. We are starting with ES 253. Now I have no idea what the atomic number of that is, so let's take a second to look that up. Oh, there it is, atomic number 99. So that means it's got 99 protons plus a mystery particle. Cool, okay. This says that it's going to make MD 256 plus, what did it say there? A neutron. So when I talk about a neutron, there's my symbol for a neutron. It's got a mass of 1. It's got a charge of 0. Okay, cool. MD, let's see, what is the atomic number of MD? 101 when you find it. Okay, cool. So from here, this is actually pretty easy. We need physics principle, let's see, I believe it's physics principle 8. Maybe I should double check that real quick. Where's my data sheet? Physics principle 8, perfect. Conservation of nucleons for the top numbers. And physics principle 7, conservation of charge for the bottom numbers, for the charges. Cool, so let's, doesn't really matter which one we do first. So I've got 253 nucleons on the left side, and let's see, I've got a total of 257 on the other side. Okay, so that means I have 4 more on the other side. I need an extra 4 over here. Could probably actually already guess what that is, but let's be really specific. So I've got 99 protons on the left so far, and I've got 101 protons on the right. That's a difference of 2. I would need to add 2 extra protons to the left-hand side. Where's my eraser here? In order to make that physics principle 8 and physics principle 7 hold true. So what that means for us, well, what's got an atomic mass of 4 and an atomic charge of 2? That sounds like an alpha particle. So it must have been an alpha particle that that smashed into that Einsteinium 235. Very cool. Oh, look at that. I had the answer already up there for me. Cool. So actually into fission and fusion. These are still nuclear reactions that we're talking about here, and they're still going to require equations and things like that. It's Enrico Fermi in 1938 that first discovered fission reactions. Now, 1938 is a pretty important time in our world's history. It is the very, very, very beginning of World War II. I don't actually know the specific date that World War II started. I'm sure some of you that have been in social studies more recently know better than I do. But 1938 is right towards the start of that World War II. And we know in World War II that nuclear weapons were becoming really big. We're going to try and focus more on the positive side of things, but there is a really, really also quite negative side of things with the arms race that happened in World War II. And if you actually look up some of the scientists, they were sort of treated like gold, but also sort of not at all, in that they were kidnapped and sometimes forced to do work that they really didn't want to do, like create bombs. But anyways, okay, back on track here. A fission reaction occurs when a large nuclei splits into small. Because remember, we talked about fission is like cracks and breaks and stuff like that, or fissures, sorry, or cracks and breaks. So it's cracking, it's breaking apart into smaller things. So here's sort of the idea from this. This is the big idea. So I've got a nucleus. And the nucleus may already be fairly unstable, but I have a slow enough moving neutron that attaches to that nucleus. And a very, very, very common one for this is uranium-235. So that slow-moving neutron bombards a uranium-235 nucleus. It would very briefly, because we're just adding one extra neutron, very briefly become uranium-236. I believe uranium has a number of 98, atomic number, sorry, of 98. Uranium-236 is ridiculously unstable. So pretty much immediately it splits into two smaller nuclei, and in doing so usually gives off 1, 2, 3 neutrons. Now those neutrons are very, very, very fast moving, typically too fast moving to get another reaction going, but if they're slowed down, if they're slowed down, they can go through another. And this is sort of our idea of a chain reaction. So if it takes one neutron to interact with one nucleus, and each reaction gives off 1, 2, 3 different neutrons, that means that each one reaction can make 3 more fission reactions happen, which means it can split apart. The next one gets split apart, the next one splits apart 3, and so on and so on and so on. It goes crazy really, really, really quickly. If you want to check out some YouTube videos of this, I thought I had a little, there it is. Fission chain reaction, honestly, just look it up. You don't necessarily need to find this one. It's just an animation to kind of show what's going on. So yeah, that's sort of the scoop. Fission reactions start with a slow-moving neutron, and this is the actual, or one of the actual things. Start with a slow-moving neutron attaching to, a lot of times, uranium. Oh, it's 92, not 98. My bad. 92. I was kind of going off memory there. Sorry, folks. Slow-moving neutron attaching itself to a uranium-235 nucleus becomes uranium-236, immediately splits apart into 2 smaller nuclei. Oftentimes you'll see barium and krypton. They're very, very common. And then of course we have 3 neutrons being given off, and sometimes we see that gamma radiation being given off. Cool. There it is. There it is. There it is. Very good. Okay, chain reaction. So let's check this out. Uranium-235 is bombarded with a slow-moving neutron. Okay, that's what we just talked about, and I now remember that uranium-235, 235, and it has an atomic number of 92, plus a neutron. So a neutron has 1 nucleon, or is 1 nucleon, with no charge. Cool. It then splits into 2 smaller nuclei. One is ZR. Now I got to check ZR. Is ZR zirconium, or is it zircon? I always get those kind of mixed up. It is number 40, zirconium. Good, good. So let's see, that makes ZR96. It's number 40. Oops, 40. And 3 neutrons. So I'm going to say plus 3 neutrons. We want to determine the other daughter nucleus. So what's the other nucleus that it makes? I'm just going to throw a question mark there. Again, we're dealing with physics principle 8 for those top numbers, physics principle 7 for those bottom numbers. So let's see. On this side of the equation, I've got 236 nucleons. On this side, I need 236 nucleons. So let's see, I got 96 plus 3 plus a question mark has to equal that 236. So it must be, I believe it's 137 is what we're looking at there. So 137 plus 3, 140 plus 96, 235. Nice. Okay, perfect. Perfect. Okay, then the bottom numbers. Okay, so let's see, I've got 92 positives on this side. I need 92 positives on this side. So far, I've only got 40. Oh, that's easy math. That's a lot easier math. Anyways, I should have 52 positives on this side. Now, all I got to do is figure out what's got 52 protons. So we look back at our periodic table here, 52. Ooh, tellurium, Te. Better get the felt pen back. Te. So the other daughter nucleus, I better make sure I'm spelling this right. Tellurium 137. Very nice, very nice. Now you've done all of this before. It's just the ideas are a little bit different, right? We have done these nuclear equations before, just the ideas. One little note with this is each time a nuclear reaction happens, so each time one of these fission reactions happens, a lot of energy is released. Now you might calculate the energy and you might see like, oh, 10 to the negative 12 joules. You might think, oh, it's not very much energy. But when you take a chunk of uranium and do it, it makes a ridiculous amount of energy. It's small for an individual nucleus, but it's a lot when you're talking an actual sizable chunk of uranium. So if we're thinking about this, how could we determine the energy? Well, if you're thinking physics principle 6, conservation of mass energy, that's a good thought. Our total mass energy before is equal to our total mass energy after. So before, let's pretend that these things are kind of at rest, right? So we've got delta mc squared, because where does the energy come from everything else? Well, it's gotta be from the mass defect, right? And the reactants will have a slightly bigger mass than the products. Let's see, that's going to be equal to the kinetic energy of the zirconium plus the kinetic energy of the tellurium plus the kinetic energy of the neutrons. Just an N for neutrons, I guess. All three of them is what we should look at, plus possibly some photon energy. Probably not usually, if I'm being honest, in our course, but sometimes. And then if I look at my mass defect, that's something that I need to look at. It is the absolute value, because remember, it doesn't matter which you subtract. It's a total mass of the reactants minus the total mass of the products. And even if you do that backwards, you do products minus reactants, doesn't matter, it's going to end up the same number. It's just the difference between the two. Just take the absolute value. But you do have to add up the total mass of all the products, all the reactants, and then subtract the two, which is a little bit painstaking, but doable. So next thing to talk about here, we've got an idea of these nuclear fission reactions, and we know that they give off a ton of energy. Let's check out how we actually use that energy in a productive kind of manner. So in a nuclear core reactor, we use Enriched, and this is like the CANDU reactor in Toronto and many other nuclear reactors around the world. We use it to generate electricity and use it to generate power. So inside the reactor, there are enriched fuel rods. I looked this up a long time ago and don't really remember what's what, but I believe enriched for this is something like 5 to 10% uranium-235, and then like 95 to 90%, 90 to 95% other stuff. If you're ever to make a nuclear bomb, I think you need like, and this is going back to that 40s, 50s stuff that World War II things, it's something like 95 to 98% enriched, like much pure. So anyways, You need a higher concentration of uranium-235 that's ordinary, just pulls out of the ground. So you need it to be enriched. The other thing that you need is some slow-moving neutrons. So you need a source of slow-moving neutrons, which are not exactly the hardest thing to find. And those slow-moving neutrons need to interact with the uranium, which is great. For each single reaction, so when it interacts with the uranium, for each single reaction, remember you get 3 neutrons. Those 3 neutrons are moving at too high of speeds to really collide and really attach with other uranium-235 nuclei, though. So too high speeds. They need to be slowed down, right? They need to be slowed down, or they're not even just going to attach. They're just going to glance off of the uranium-235. So what we do is we put that in heavy water. Now, heavy water is just water, but instead of using hydrogen 1, we actually use hydrogen 2 in that water. Now, a fancy name for that is deuterium, and it is, again, it's just water. It's H2O with a bent shape and all of that. It's just a little bit heavier because we've got 2 extra neutrons for every water molecule. Right, or 1 for every one. So what this does is it interacts with those neutrons and it actually slows them down. When it's slowing them down, their kinetic energy is transferred from the neutrons to the water, though. So that water heats up. So it slows it down and heats up at the exact same time. It's kept under really high pressure, so it doesn't actually boil. The higher the pressure doesn't boil. You can check out videos of like deep sea volcanoes and stuff. The water gets up to like 200 degrees Celsius. It doesn't boil, but really, really high temperatures. And then what we do with this water. So 1, the neutrons are now slow enough that the chain reaction can actually continue. 2, we actually take this water, so it's in a sealed system. So you'll notice all this water is in a sealed system. Here's the reactor core. The hot water goes up, it goes and it runs through water that is at regular pressure, regular just 1 atmosphere, or roughly 1 atmosphere, and then it gets pumped, it gets cooled, and then it comes back. So it's that cycle. Hot water comes up, it gets cooled as it goes through the regular water, and then it comes back. But as it goes through the regular water, it causes it to boil, right? That's because it's just at regular plain old pressure, so it causes it to boil. Now, you probably know, you might remember this from Science 10, that steam is something like 1,600 times bigger than liquid water. So it creates a ton of pressure up there. That pressure actually spins the turbines, which run the generator, which is just, we've talked about generators in Unit 3, which then creates the power, which is then sent to, homes and factories and whatever else. So pretty cool. Now, controlling these ones is kind of the important thing, right? And I'm sure you've seen videos and heard of things where they've gone uncontrolled and it's been a disaster. So if more neutrons are being emitted than are being lost and absorbed, you say that it's gone critical. So too many neutrons are flying out there. The reaction is going to be going too fast, so too many uraniums are going to be reacting. That's not a good thing. Definitely not a good thing. You do want the chain reaction to continue, but you don't want it going too fast. So it's actually a fairly simple solution. They take control rods. Control rods are made out of things like boron and cadmium that absorb neutrons and don't care if they have extra neutrons. And all you do is when it starts going too fast, you lower the control rods in between your fuel rods, and it slows things right down. You want to speed it up? You lift those control rods up. Now, I'm making this sound really, really simple. The technicians that do this are highly trained. I would not want to have any part of this without some serious education and training. But still, it is in its essence fairly straightforward. So here's some advantages of fission reactions. Some nice things about these fission reactions. They're pretty easy, right? They're easy to start. They're kind of easy to control as long as people know what they're doing. They have a ridiculously high energy yield. So 1 kilogram of uranium provides about 2 million times the amount of energy that 1 kilogram of coal provides, which is crazy. That's a lot of energy. Other ideas is, and this is one that we didn't really show, other advantage is that there's no carbon dioxide, which we know is a big issue with our atmosphere right now. So no carbon dioxide is actually being given off from the production of electrical energy. Disadvantages is the spent fuel rods are still pretty radioactive. Now, I don't know if this is a real picture or not, but this guy, I would, if those are full and that's a real picture, I feel bad for that guy. The water itself can also be contaminated and needs to be disposed of, which is another issue. So typically what they do is they actually encase things in like concrete, lead, steel to protect from gamma radiation, and then bury them in abandoned mines, which is not the greatest solution, but it is a solution. Another issue is uranium is not really a renewable resource. You know, and this is one of those things, depending on who you talk to, some people say you can have about 200 years of uranium left on the planet. Other people say, well, if we start to mine the ocean, well, we can have a lot more than that. If we improve our reactors, we can have a lot more of that. So like 30,000 years worth of energy, 60,000 years worth of energy, that's all of a sudden significant. 200, but 60,000 years, that's a long time. Okay. Next thing, fusion reactions. So a fusion reaction, we already kind of talked about this. This is when two small nuclei form a larger nucleus. This is what's going on in our sun. And actually, our sun is not big enough or hot enough to make it happen naturally. So it's relying on quantum leaps. I learned this the other day. It's pretty wild. But the fact that, you know, the individual nuclei are behaving both as particles and as waves, and they jump in and out of each state, and sometimes they jump in to be close enough. But anyways, that's a whole nother story that you might want to check out. Pretty interesting stuff. But these are the reactions that happen in the sun. So we've got helium-2 and helium-3 coming together, or sorry, hydrogen-2 and hydrogen-3 coming together to make helium-4 and a neutron. This is the equation for a hydrogen fusion reaction. Now, there are other types of fusion. They just don't typically happen in our relatively small sun. But this is the one we got to know about for our class. Hydrogen-2 and hydrogen-3 make helium-4 and a neutron. Now, you might remember this, helium-4, that's also an alpha particle. Also an alpha particle. Cool. So the advantages of these fusion reactions is that they have like really stable and really safe byproducts. Like you're making helium and you're making a neutron. Those are easy to control. Those are not really that dangerous. That's cool. Other advantages, we have lots of fuel. So deuterium, or hydrogen-2, can be extracted from water, like just regular plain old ocean water, and you have an unlimited supply. Hydrogen-3, or tritium, could be bred from lithium, which could last for thousands of years or more, which is pretty cool. The disadvantage of this, the big disadvantage, is that you need ridiculously high temperatures in order to overcome the force between those protons, right? Because, you know, positives don't like to be next to other positives. So there's a very large electric force, and you need a lot of energy to get those two things together, to get them close enough so that our strong nuclear force takes over. And typically we have like 100 million degrees is what we're looking for. Now, that being said, the big issue with this is we can't actually have that happening on our planet. It loses, or at least we don't have the technology for it right now, it loses energy faster to its environment, faster than it's being given off. That's the big issue with this. So there's two types of fusion reactors at this time. Again, both of them really lead to, or neither of them, I should say, lead to a self-sustained fission reaction because they're giving off more energy into the environment than it takes to get those nuclei together. So there's magnetic confinement, and then there's inertial confinement. So magnetic confinement is essentially under really, really, really high pressure due to magnetic fields. The hydrogens are squished so close together, and then they're put into circular motion, and that's where the nuclear reaction happens. So we use magnets to squish the hydrogen together in circular motion, and it creates helium. The other one is inertial confinement. This one's kind of neat. Essentially what they do is they blast hydrogen, so there's samples of hydrogen here. They blast it from all directions with lasers to kind of hold it up and to push it together that allows heating it and allows it to remain in the center, so it's not actually touching things due to inertia. And of course this leads to, I believe this is either Spider-Man 2 or Spider-Man 3, where who knows if it was actually magnetic or inertial confinement or some kind of combination of both, but turns out Doc Ock actually figured it out before anybody else. Okay, last little game to play here, last little bit. Fission, fusion, or both? Which one is induced by a slow-moving neutron? Fusion, absolutely. Which one experiences a mass defect? I said which one, which was a bit of a trick. It's actually both. Where does the energy come from? Well, both comes from the mass defect. Which one has stable byproducts? Fusion. Which one experiences a transmutation, so change in the type of nucleus that we've got? Well, both of them. We saw that on both of them. Which one requires, not produces, but requires really high temperatures? Fusion. And then can produce neutrons as a byproduct. So can produce neutrons as a byproduct. Turns out it's both. So fission produces 3, fusion usually produces 1. That being said, fusion, if you get to big enough stars, you can like fuse together to make iron and heavier elements and stuff like that. So there you have it, folks. Do a bit of practice and let me know how things go, and we'll talk to you again soon. Bye for now.